Think about it for a second. Every car, every skyscraper, every single tool you've ever held in your hands, it all started its life as just a rock. So today, we're going to pull back the curtain on the incredible industrial alchemy that turns that plain old rock into the very metal that built our modern world, iron.
So, that brings us to the big question. Iron makes up a whopping 5% of the Earth's crust. I mean, it is everywhere. But here's the catch. You almost never just find it lying around in its pure metallic state. Instead, it's chemically locked away inside ore, bonded tight with oxygen. So the real puzzle isn't finding it, it's how in the world do we break it out of that mineral prison?
Okay, so here's our game plan. We're going to tackle this in 5 parts. First, we'll lay out the challenge. Then, we'll look at the recipe, the key ingredients. We'll check out the massive reactor where it all happens, watch the transformation by fire, and finally, see what actually comes out at the end of the whole process.
All right, first things first, let's really get a handle on the problem. The iron we want is trapped as iron oxide, and it's not alone in there. It's all mixed up with a bunch of other useless rock and minerals, which we call gangue. So the goal is basically to launch a kind of chemical rescue mission. In that rescue mission, it's really got 3 key parts. First, we need something called reduction. That's a chemical reaction where we use another element to literally steal the oxygen away from the iron. Second, we've got to melt everything so the heavy, pure iron can separate and sink to the bottom. And third, we need to clean it all up by getting rid of that useless rock, the gangue. So, to pull this whole thing off, we need a very specific recipe with 3 crucial ingredients. You can think of them as the 3 main characters in this whole industrial drama. Let's meet them.
Okay, ingredient number 1, the iron ore, obviously. This is our starting material. And it contains both the prize, the iron atoms we're after, and the problem, all that worthless gangue we need to get rid of.
Next up, we've got coke. Now, this isn't the drink, it's a purified, high-carbon form of coal. And let me tell you, coke is the absolute hero of this story. It does 2 critical jobs. First, it's the fuel, creating the mind-boggling heat we need to melt metal. And second, it's the chemical agent that actually does the work of freeing the iron from the oxygen.
And rounding out our trio, we have the flux, which is usually limestone. You can just think of this as the cleaning agent. When it heats up, it acts like a chemical magnet, attracting and latching onto all that rocky gangue. This forms a whole new liquid substance, which is going to be super important for the separation process. All right, we've got our recipe. So where do we actually cook all this stuff? Well, it all happens inside a massive, continuously running chemical reactor called a blast furnace. And when I say massive, I am not kidding. These aren't just big ovens, they're towering steel structures, sometimes as tall as a 10-story building. And they are designed to run nonstop, 24/7, for years at a time, just constantly churning out molten metal. You know, the real genius of the whole design is this constant 2-way traffic. From the top, you have layers of ore, coke, and flux slowly trickling down thanks to gravity. And from the bottom, you have a powerful blast of superheated gas blasting upwards. This countercurrent is what makes the whole thing so efficient, creating these different chemical reaction zones as the materials pass each other. Okay, now for the fun part. Let's imagine we're following a single chunk of iron ore on its journey down into the belly of this beast as it passes through hotter and hotter, more intense chemical environments. So as our little chunk of ore starts its descent, it first hits a drying zone at around 350 degrees Celsius, where any moisture just boils away. Then, as it gets hotter, the really critical reduction phase begins, and the oxygen starts getting stripped off. Lower still, the now spongy iron starts soaking up carbon from the coke. And finally, way down at the bottom, in the hottest zone reaching 1800 degrees, the coke itself combusts, providing that intense heat and the gases that drive the entire system. So if you boil all that chemistry down to one key action, it's this. Burning the coke creates carbon monoxide gas, and this gas is incredibly hungry for oxygen. As it rushes upward, it meets the iron oxides coming down and just aggressively rips the oxygen atoms away, leaving behind little droplets of liquid iron. So after all that intense heat and pressure and chemistry, the transformation is complete. The materials have finally made it to the bottom of the furnace in liquid form. But what do we actually make? Well, it's finally time to tap the furnace and see what we've got. And what comes out isn't just one thing. It's actually 3 totally different products. The main event is the pig iron. That's our liquid iron that has now soaked up some carbon. Floating on top of that is the slag. That's our flux, which is now combined with all the impurities from the ore. And coming out of the very top of the furnace is the leftover gas, which is still pretty useful.
And this is where you can really see just how smart the whole modern process is. Seriously, nothing goes to waste. Over 90% of that liquid pig iron goes straight to a steel mill to be refined. The liquid slag is cooled and then used to make things like cement and concrete. And that leftover furnace gas, it gets captured, cleaned, and used as fuel to heat the very air that gets blasted back into the furnace. It's this incredible, self-sustaining loop.
And there it is. The blast furnace is just this incredible testament to human ingenuity, a continuous river of fire that turns stone into the skeleton of modern society. I mean, this process literally built the industrial age. But as we look to the future, the really critical question becomes, how do we evolve this carbon-heavy giant for a more sustainable world? Now that is the next great challenge.